This is lesson 3.2, physical properties. So periodicity refers to the properties of an element that repeat periodically. For example, atomic and ionic radii, electronegativity, ionization energy, all of which repeat periodically. So all of these properties depend on something called the effective nuclear charge, which we show as ZEFF, or Z effective, or the atomic number effective. So the nuclear charge is just the atomic number, the number of protons. However, the electrons that are on the very outermost edge of an atom are actually shielded and repelled by these electrons that are inner electrons. So if you consider the atom and consider the multiple energy levels, the first energy level you have these electrons and they're shielding these outer electrons because negatives repel negatives. So these outer electrons do not feel the total nuclear charge from the core, from the nucleus, because they're being shielded from the inner electrons. So the effective charge is the charge experienced by the outer electrons. It's not that full nuclear charge because of the shielding. So here's an example in sodium. Sodium has 2 electrons in the first energy level, 8 in the second, and 1 in the third. And you can see that this last electron is not going to feel the same effects of the nucleus as the inner electrons because of the shielding. So to find the shielding, you're going to take the total number of electrons, so 11 for sodium, minus the electrons in the inner energy levels. So 2 in the first and 8 in the second is 10. So the effective nuclear charge that is felt by this outer electron is really 11 minus 10, so just plus 1. So as you go across a period, the nuclear charge increases because protons are added and the effective nuclear charge stays the same because the inner electrons don't change. So as we go across, okay, from sodium to magnesium to aluminum to silicon, we can see that the nuclear charge will increase because we're adding more and more protons, but the effective nuclear charge will stay the same because the shielding electrons will not change. Down a group, the nuclear charge increases, but the shielding also increases, so the effective nuclear charge will remain the same. So across a period, the effective nuclear charge. So as we go across the period, the nuclear charge increases because you're increasing the number of protons. And the effective nuclear charge will also increase because the number of shielding electrons does not change. So you can see as you go from sodium to silicon, you still have 10 shielding electrons, 10 shielding electrons, 10 shielding electrons, 10 shielding electrons, but the nuclear charge is increasing. So 11 minus 10 is plus 1, 12 minus 10 is plus 2, 13 minus 10 is plus 3, and so on. So the effective nuclear charge will increase across a period. However, down a group, the nuclear charge increases, but the shielding also increases. So here, for example, from lithium to potassium, we have 2 shielding electrons, 10 shielding electrons, 18 shielding electrons. So the effective nuclear charge will stay the same down a group. The atomic radius is half the distance between nuclei. So for example, if this is a hydrogen atom and we draw a circle representing the outermost edge of the hydrogen electron cloud, and remember hydrogen is diatomic, it can bond to another hydrogen. Half the distance between these 2 nuclei that are bonded together, so half would be from here to here, that is the atomic radius of a hydrogen. So it's measured using the distance between a bonded nuclei. So remember that atoms do not have sharp edges, so it's kind of difficult to measure the atomic radius, and that's why they do it when they're bonded to another atom. And for a list of atomic radius data, please reference Table 8 in your data booklet. Now, as we go down a group, the radius increases because as you go down a group, remember you're increasing energy levels. So, for example, lithium, you have 2 energy levels, sodium's 3, potassium's 4. So as we go down, your atomic radius is going to increase. However, as you go across, your effective nuclear charge is going to increase, like we just said. And so as your effective nuclear charge increases, it pulls harder and harder on those valence electrons. And so what happens is those valence electrons are pulled in slightly, which decreases your atomic radius across a period. So here's a question for you. Why are there no values for the atomic radii of noble gases? And this is a tricky question. Yes, if you said the reason there's no atomic radii for noble gases is because the noble gases do not form bonds, so there's no way to measure the distance between bonded nuclei, then you are correct. Now, ionic radii are different than atomic radii. So positive ions, ones that lose an electron, are going to be smaller than their parents. For example, here's lithium after it lost an electron. Here's sodium after it lost an electron. Because you're losing that outer electron, which means that the remaining electrons are pulled closer and tighter to the nuclei. Negative ions are going to be larger than their parent atoms because you're adding an electron in, which is harder to be held by the nucleus, and you're increasing electron-electron repulsion. So the electrons are spreading out farther from the nucleus. So you can see that as you go across, your ionic radius is going to get bigger, and it's also bigger compared to your parent ion. So here we have a positive ion, smaller, positive ion, smaller, positive ion, smaller, positive ion, smaller, negative ion, bigger, negative ion, bigger, negative ion, bigger. Ionic radii will decrease from group 1 to 4 for positive ions. So as you go from group 1 to group 4, you have the same electron arrangement of 2, 8 in the inner shells. So you're increasing the effective nuclear charge, so your ionic radii will decrease. So as you go from sodium loses an electron, magnesium loses 2, aluminum loses 3, look what happens to your radii. It gets much, much smaller because your effective nuclear charge is increasing. And ionic radii will also increase down a group because as you go down a group, of course, you're filling more and more energy levels, so you're getting bigger and bigger and farther apart from the nucleus. Okay, so describe and explain the trend in radii in the following ions. So you have oxide, fluoride, neon, sodium, and magnesium. So if we compare neon, which is neutral, to sodium, which is positive, and magnesium, which is positive too. So magnesium now has 12 protons pulling only 10 electrons. Sodium has 11 protons pulling 10 electrons. Neon has 10 protons pulling 10 electrons. Fluorine has 9 protons pulling 10 electrons. And oxide has 8 protons pulling 10 electrons. So we can see that magnesium is going to be the smallest because it has the most protons pulling on those 10 electrons, followed by sodium, followed by neon, followed by fluorine, followed by oxygen, because oxide only has 8 protons, trying to pull in all 10 of those electrons. Another thing that we can see that changes periodically is ionization energy. So remember, ionization energy measures the attraction between the nucleus and the outer electrons. It's how much energy would be required to remove an electron. So as you go across a period, ionization energy increases because your effective nuclear charge is increasing, which means that it's getting harder and harder to pull an electron from the nucleus. As you go down a group, the ionization energy decreases because the effective nuclear charge, remember, stays the same, but you're getting farther and farther from the nucleus, so it's easier to pull off those outer electrons. Another property that changes periodically is electronegativity. And remember, electronegativity is the ability of an atom to attract electrons in a covalent bond. So it measures the attraction between the nucleus and the bonding electron. So here, for example, is HF. And remember, fluorine is the most electronegative atom in the periodic table. And you can see that fluorine pulls the electrons in this bond towards it and away from hydrogen. So electronegativity increases from left to right across a period, because as you go across a period, your effective nuclear charge is increasing. And it decreases down a group, because as you get farther and farther away from the nucleus, your attraction is reduced. The melting point is also a property that can compare within a group of a periodic table. The melting point, remember, depends on the type of bonding, because it depends a lot on intermolecular forces. So we can see there's two groups that we like to compare, group 1 and the halogens. And in group 1, as you go down the group, the melting point decreases. But in the halogens, as you go down the group, the melting point increases. So this seems kind of counterintuitive. So what could be happening here? So if we talk about the halogens first, group 7, remember these are all held together by van der Waals intermolecular forces, because they're all nonpolar, and so they only have those instantaneous dipoles. So as you get bigger and bigger, you have more electrons, so you have more instantaneous dipoles, meaning that your van der Waals forces are increasing, which makes your melting point increase. It's harder to pull them apart. If we talk about group 1, however, these are all metals, so we have metallic bonding. And as we go down further, down group 1, those nuclei get farther and farther apart. So it's harder for them to pull onto that, to hold on to that sea of electrons. It's easier to separate, and so their melting point decreases. As we go across a period, the melting points generally increase, but then they go down, and then they increase again, and then they go down, and then they increase again. So why would this be? Well, the reason this happens is because the bonding is metallic, and then it's covalent, and then of course you're talking van der Waals here in London dispersion, and then of course the same thing again. So it all depends on the type of bonding.